to get all of the lecture into the week unless I canceled the plan for Tuesday and just lecture instead. Tuesday being the day you were going to turn in your solar house plans. So instead, I'm going to have to push the solar house plans to next week, which coincidentally might help those of you who cannot plan your lives. Nicholas Blondell. So for everybody who has their game together and already finished your solar house, well, bravo, you can just sit on your hands for an extra week. To most of you who have not taken the time yet, well, by coincidence, I've saved your grades. But it wasn't my intention, and don't get used to it. I didn't do this to be friendly. I did this because I was too stressed out about finishing the lecture. But I guess you're glad I was stressed out. Are there any questions about the solar house plans which are due next Monday? Yes?
In terms of the key, is that so we have like a little maybe star or something on the eaves, and then on the key it says what type of passive solar energy it is?
Yes, except you don't need to explain it, and instead of using a star, you should use sequential numbers. So 1 would be solar geometry, and then you show where your windows and eaves are. Then number 2 would be solar mass. So you put a little 2 if you have stone floors, or a little 2 if you have concrete walls.
And should the key be on a separate piece of paper?
Yes, 8 by 11 for the key. Any other questions? Yes?
When you test the houses, are you keeping the light or whatever in a constant place, or are you moving it to go throughout the day?
There is a constant summer location and a constant winter location. That's all. Direct shot. I'm so proud of me. William?
There was one of the 8 things that I wasn't sure what it was. Oh, it was like thermal ventilation?
Yes.
How is that? Can you just make me explain that?
Convection.
Okay, so isn't that... There were 2 bullet points.
There are 2 separate types of ventilation. There is passive, which is like airflow, like just letting the wind blow and the wind will blow.
Like into the house?
For example.
Okay.
No,
And separately from this, there is ventilation that doesn't rely on wind. It's called convection, where hot air will escape because it's like a hot air balloon trying to float away. And that creates a pressure drop in your building, which that air has to be replaced from somewhere. So you can suck in cold air like from behind your house where the shady, wet grass is or something. What else?
For the labeling, we just put it, the number wherever it is on the house.
Yes, wherever the number shows up in your schematics.
No explaining.
No explaining.
It could be like 2 separate times, like within.
Yes,
a
it can.
same number.
Yes, it's the same number because it's the same concept in different features of your plan. Yes. Yes?
If we want to take a minute and just look at the other demos and just kind of make sure.
Sure, you can bring me a rough draft and I can give you feedback if you'd like, just as long as it's not interrupting class time. Next.
So not the 3D, but the other one should look like a floor plan, like that an architect does, or a designer.
Something like that, yeah.
So just from the sky with like no roof.
That's right.
Really?
That's right. Like a sky with no roof. Yes. What else? Innocent bystander, sorry. Anybody else? Okay. Now, students, we wrap up alternative energy. Because I don't know about you, but when I looked at all that stuff that was on the board on Friday, I get this. Did we finish all the geothermal and stuff? Yeah. I get this feeling sometimes, like I feel like I've been ripped off. Like, why aren't we just doing all of that?
Wait, we didn't go over geothermal.
We didn't go over geothermal?
No, we stopped it right there.
We stopped at the...
Did we do wind?
Yeah.
So I'll show you geothermal very quickly. This is number 30. Did we do anaerobic respiration biomass?
No.
We're on number 34. We'll do these very quickly. That was kind of funny. He said, oh, shoot. Biomass my daughter does those. She does headstand into back bend, and then she walks her feet up and goes, stands up. She's so ripped. She's so ripped. Like a little stringy, sinuousy muscle with a couple little bones in between. All right. So, and a lot of character. Okay. So number 34 is biomass. As far as you need to know, in terms of energy sources, you either light stuff on fire to spin a turbine, or you find some sort of anaerobic decomposition to make methane. You can use the carbon bonds in trash, the carbon bonds in sewage or in sludge. You can use the carbon bonds from agriculture or lumber waste. But anaerobic decomposition makes them into methane. You light that stuff on fire, and remember, the CO2 you get is current CO2. That's not global warming. That's current. Did you not sleep or something? You're always yawning, but you look more sleepy. I mean, you look fabulous, but also sleepy. Whatever. Go ahead.
The CO2 that goes into the air is current, even though like all that CO2 wouldn't be in the atmosphere if you had to like, you know, it's like in the biosphere, but it's locked up in the biosphere rather than being in.
But it came from somewhere.
Okay, but like it would never all be in the atmosphere at once.
No, but you have to remember that you've already cleared up the land to put it on fire, so by clearing up the land, you've given the space for the atmosphere to park itself.
How does the atmosphere?
You know, new growth.
Oh, okay.
So if you mean biomass by removing habitat types, then you're right, that's not renewable. But if you assume that that biomass is harvesting and regrowing simultaneously, then it is short cycle. The other question is there a shift in habitat types? Like, are we turning rainforest into city? And that part is essentially new carbon, because you're decreasing the amount of carbon that lives on terrestrial biomass. That's true. Okay, so number 34 was, quite simply, anaerobic decomposition makes methane, and congratulations, no climate guilt. Now, number 35 does not work everywhere. But are you all aware that somewhere below the Earth's crust there's a layer of red, hot magma? And in some places, that magma is closer than other places. Like in Santa Barbara, that magma is nowhere near you. It's like 30,000 feet down or something. I don't know. It's a long way down there. But there are places like Iceland where that magma is very near the top. You can tell where it is because you'll find little puddles of hot water.
And right?
Yes, geothermal pools are places where groundwater hits magma, or technically it hits the hot rock above the magma. And because it's hot, that water gets really heated and expands and bubbles to the surface as a hot spring. So there is actually one little hot spring right behind these Camino. And there is another one up near Gaviota Peak. And there is the little one on Hot Springs Trail. You know, Hot Springs Trail.
How close to the surface is it?
It's a really good question. I don't know if that's like a fluke of geology or if there actually is some high magma potential in Santa Barbara. I actually don't know about that. But there are some places where the crust is very, very thin and there's a lot of magma. Like Mammoth Lakes, California, where everybody likes to go hot tubbing. Oh my God, the Whitmore tubs. And in these places, you can make what's called geothermal electricity, where you take cold water at the surface and you pump it down until it encounters the hot rock on top of the magma. And when that water comes back to the surface, it's like a man-made hot spring. So you inject cold water and it comes out hot. You know, like the geysers in Yellowstone. And if it comes out really hot, you can do some fancy plumbing and stuff. And then you can use that heat to make steam spin a turbine. Yes?
Doesn't geothermal energy, or the capturing of geothermal energy, doesn't that displace all the heat and cause seismic activity?
Yeah, so there's this new theory that that energy has to go somewhere. So by cooling down the Earth, the theory says that the rocks will move differently. Now, I'm not really sure how much earthquake potential this makes, but it does seem to be a real thing. The amount of tectonic activity generated by this is probably kind of small. But so far, it seems to be a real, significant, measurable, not make-believe scientific fact. The reason that I'm making all this mess is because there's something I want to show you over here. I hope you'll forgive the distraction. That somewhere else? Come on. You need water? I have water in the fridge. You take a little while. Okay. This cool map right here is a map of all the tectonic plates on Earth. And you can see these underwater mountain ranges. See those? The rifts. That's where the plates are spreading apart from each other. Where they slam into each other, we get coastal mountain ranges. Like the Andes and the whatevers and these and all that stuff.
Wait, so if they're pushing away, they're still on mountain range?
Yeah, because I don't know if you guys have ever noticed when you get a scab, what happens when you have a scab that bends? What happens in the middle of that scab? Cracks, and then what comes out of it? Juice, goodness, juicy goodness.
Bloody pus.
Bloody pus blood? Yes.
Might be a stupid question, but could our Earth get bigger by the plates stretching out and then it like stretching out?
It has to come from somewhere, so whenever you're going like that, somewhere else it's going like that. Yes?
So it's the same thing, just like underwater, or something like the same.
Yeah, precisely. That's what that is. Now, here's the news flash. The reason I mention these plates is because this always happens underwater except for one place. Iceland. Iceland is the only terrestrial splitting plate. So, and what's awesome about Iceland is they have so much splitting scab, so to speak, that all of that magma near the surface lets them make a tremendous amount of electricity. They are the world's only nation with carbon neutral electricity. But get this, if they can figure out the wire, they will be the world's largest exporter of energy by the end of the decade. Iceland.
How do you
No, how to stretch the wire from Iceland to the British Isles, France and Germany. They could export more energy than Saudi Arabia, but unlike Saudi Arabia, it would be global warming guilt-free. So the international community is like, wait, you guys can produce enough energy to like make electricity for all of Europe? And they're like, sure. We have big split scabs, so to speak. Yes?
Wouldn't that screwing along the wire for the British Isles be a waste of energy?
For sure, that's why I said there's some questions about how to insulate the wire correctly and whatnot, and maybe make it a high-tech conductor. But remember, who cares? It's free electricity. I mean, it costs some materials to build the reactors and stuff, but once you have your power plants built, you don't have to add fuel.
We need to add more.
Not if you recapture your steam. And by the way, it's Iceland. It's not like they're worried about water. Yeah.
So does by pumping cold water down into the warm magnetic rocks and then having that water like take heat from the rocks at a faster rate than we normally escape, that's where the seismic activity comes from? Because
Right.
we get way more heat out than we normally come out at that
Right,
rate.
so you shrink rocks.
So is that like bad in the long term? Like the Earth's processes and all that heat. that
In the
it-
real long term, probably not. The only question is, does that create dangerous seismic activity? And technically, all that does is increase the likelihood of very, very, very small murmurs, which in the long term might avoid mega earthquakes by dissipating energy in little hits instead of the big rumbles. Or on the flip hand, all those little rumbles might launch the slips that cause mega earthquakes, and that's the only question mark, really, about tectonics and danger. Thank you for going direct. Yes?
I know they talk about fracking as the same problem, but like, what is the like actual difference? Like, I guess there's like serious earthquakes, like 5.0s that are happening like Oklahoma.
Actually, we can't attribute 5.0s to
Well, yeah,
fracking.
That's their argument, right?
Well, I haven't heard that argument. All that we know about fracking is that when you're done with the fracking fluid, you got to do something with that nasty liquid, and you can't discharge it on the surface because it's too much nasty liquid. So we do what's called deep well injection, where we drill these giant holes and we inject that water way deep in the ground. And so the fear is that by adding, the dirt, that liquid is a lubricant. That's what it's used for in mining.
Yes.
So once we get rid of it, the fear is that we are injecting lubricants into the tectonic layers. And so we have seen already, and it is known and measured, that deep well injection sites do set off small earthquakes. Like I was telling William, it's a toss-up whether those small earthquakes can start big earthquakes or if they avoid big earthquakes by dissipating.
So it's not,
tectonic buildup.
the initial displacement that would be doing it, it'd be long-term injection.
It's not the fracking that causes the earthquakes.
Oh, okay.
It's the disposal of the fracking fluid.
All right.
It's a separate process. After you're done all your fracking, and who cares, fracking over here, you still have a bunch of fluid left over, and to get rid of it, they inject it, and that's the risk. Okay. Anybody want to talk more about geothermal? Because I'm sorry, we're like 30 minutes delayed. We got to make that up in about 25 minutes of class. Here goes. When I see all these things, I wonder, well, which one do we take? Come on, let's do this. And get ready to take a bunch of notes. Well, y'all just sitting there with no papers out? I have no patience for that. Of course, the cost problem is a big one. Someone has to pay for these power plants, and investors, they need their money back. Like, if you want to build, this is for all the different energies. This is at the end of 7.4. Can I help you? Please ask your question. Well, then please make that face again. That indignant, I don't know what the hell's going on in your face. Like, it's my problem that you don't know what's going on. Yes. I was just thinking about it. Okay. So the cost issue is a really big one. If you're going to get somebody's money to build a power plant, you're going to have to tell them how much money you can give them back. Any investment, they need to know what their returns are. And for a lot of this alternative energy, the returns are like, I don't know, we've never done it before. And who knows, maybe it'll be windy, but maybe not. And maybe with climate change, we'll get new cloud patterns, but maybe not. That's the funny thing. One half of the energy sector pretends there's no climate change, but the investors know what time it is, and they're really worried how climate will affect currents, wind, solar radiation.
That causes like to see an investment.
Yeah, I mean, that makes it really difficult to make a safe investment. You know, when it becomes more speculative, it becomes more profitable because less people will speculate, right? You understand that about investments, right? That if nobody's putting their money into it, if you're the only jerk that takes the chance and you win big because you're the only jerk in the game. So it's not like there's no potential for investment. There's just not a lot of clarity. Compare that with a coal-burning power plant. Like, oh yeah, you can see the other 37,000 that I have built. I can give you their average return today compared to what it was last year. These are all marginal. For investment, all of this stuff is kind of risky. That's where the government has to give away investment dollars. And it doesn't always work out in your favor. We've wasted a lot of tax dollars trying to push the investment ball. Of course, this question about risk is especially tricky when the technology is fundamentally new. The risk for a nuclear power plant, whatever that is at least well known. There's like 1,000 nerds that study the risk histories. They get all the details, they do the whole actuarial table for you. But you can't do that for new technologies because they have no track record. Then remember, there's that on-demand question. The power grid has no storage. If you turn on one microwave too many for the power grid, the whole grid goes down. You guys know that? Yeah, like right now in a split second. Like right now, if we turn on one more microwave and that happens to be 125 watts too much, between us and the next, whatever they call distribution center, the whole grid goes out. So I don't know what the size is of our grid block, but I'm pretty sure that Santa Barbara has like 2 in downtown. Or at least 2 main blocks. So if we're one of those, we would take down half of Santa Barbara with our microwave. Yeah?
What's the safe zone right now? Like how much until it's a blackout?
Oh, we always have a surplus. We're always operating at a significant oversupply. So that can't happen. And as soon as our consumption starts to creep up on that supply, they have to turn on another power plant. But this is the problem with alternative energy. Because what happens if all of a sudden your supply takes a dip because the wind just died? Or if your supply takes a dip because a cloud just came over the sun? You have to have more supply than is being used at any given moment. That's mandatory. So wind and solar, that's nice, but they're just bonus. You know, when it gets windy, guess what? The nuclear power plant guy's like, hey guys, I'm over here, I'm ready, I can do this. The natural gas is like, coach, put me in, I'm ready to go. You can't tell the baby Jesus when to make sunlight, when to make wind, but you can flip the switch and turn on the natural gas plant. That's like a 45-minute rev-up cycle, and then pow, you're producing. You know, people get really bummed when grandma's ventilator shuts off. The power companies cannot afford blackouts. It really is life or death. You know, somebody will be writing the finishing lines on their PhD and the computer goes out. Somebody's performing surgery in the ER and the lights go out. Like, it really is, the electricity supply is really life or death, like lawsuits and profit. And it's a big deal. So they cannot have a fickle supply. Then, of course, nobody wants this stuff in their backyard. A lot of times the materials are in the wrong place, or the factory's in the wrong place, or the fuel's in the wrong place. I heard a really interesting example. People made these like layers of a map. So they had a map of the United States, and they laid down one layer, and they're like, here's all the windy areas. And they laid down another layer, and they're like, here's all the sunny areas. And it filled in more of the map. And they're like, here's all the people. And they barely overlap. Barely overlap. Because you know what? Nobody wants to live where it's always windy and where it's always sunny.
A little bit.
But if you put your electricity stuff there, then you're going to waste half the electricity getting it to you. You know, everywhere you are, your power plant's probably less than 100 miles away. 200 miles is crazy far away to generate electricity. Most power is within 100 or 200 miles because, you know, you lose it all on the wire. So everybody's like, couldn't New Mexico produce all the electricity for New York? No, it's too far. They'd have to produce like 12 New Yorks to get it to New York. So these regional questions are a really big whoop. The people are not where the sustainable energy is, for the most part. You know, everybody likes to live in Santa Barbara right next to the beach, but you think Santa Barbara would let you build a bunch of tidal generation units out on our beach? Like, if you're going to do that, you got to go to that place where nobody's living on the beach, which is nowhere. Yeah.
What is like the definition of grid for like the last bullet point?
The grid is the system of wires that delivers electricity. But remember that even though there's wires across the entire United States, the grid is national. The supply to usership is short sections of that. So even though there's wires that go from here all the way to New York, you don't take electricity from New York to here. Yes?
If we have to make more energy than we need to use, but we can't really store that energy, are we just wasting that?
Yes, it gets grounded. Girls, I recommend you watch the video. The end of today is really foundational for tomorrow. Like, I'm rushing to get to the part that everybody needs, and you're not going to be here for it. Good luck with your opinion. You know, dependability is a really big question. When people are doing this cost-benefit analysis, they really freak out about how dependable your supply is. And you know, like, natural gas, like, it is dependable. Coal, like, you call the mine today, they're ready to ship. You want another coal-burning power plant? When it's built, it's running, I promise. There's no question marks in the fossil fuels. That's why we use them. They're just a safe bet. Yeah?
So the reason why coal has been so surefire is because you can ship coal anywhere to any power plant.
Yeah, I mean, rather than shipping electricity, you can ship the coal, absolutely.
And so geothermals in Iceland, so that's why it sucks.
Yeah, that's right, that's right. You know, the United States has a couple geothermal hotspots.
But not like that.
Not a lot. And we're a big old country. If Iceland has to deliver electricity to London, that's less travel than New York delivering electricity, than New Mexico delivering electricity to New York. Think about that. Like,
It's a short distance.
international electrical potential is greater than half our country's electrical potential. Yeah.
How would they even transport heat energy to?
No, they need a wire. Remember also that nobody wants to say this, but CO2 changes this game completely. You see, in our current economy, CO2 is not in the balance sheet. There's cost, there's benefit, and then there's cost and benefit in the future. That doesn't exist in our accounting. It's like a credit card bill that nobody's worried about paying. That's CO2. We don't have to pay for it because we'll be dead. You guys will have to pay for it. Just so you know, your bill is racking up. We're living on your credit cards. All the high school kids think they ripped off their parents when they steal mom and dad's gas card or something. We are living on your credit card. All of our economy depends on a problem that we won't have to fix. It's your problem. It's called climate change. Good luck with that. It really is. Economically speaking, it's a ticking time bomb. Everybody knows. But we're just not ready to do anything about it, so we just let it keep ticking.
Was it your parents' generation's problem? Or your generation?
Yeah, I mean, arguably, I think it might even go further back than that. But my parents could probably be forgiven for not knowing about it. My generation is just plain old not doing anything about it. We laugh. We laugh. As a generation, we know it's a problem. We know you're going to pay for it. But I don't care, bro. I got bills to pay. You know, like some of us are like trying a little bit, kind of, sometimes. I got compact fluorescents. For you, bro. And let's remember that there are many other factors like water impact, air pollution, the wildlife impacts. Last year, the biggest killer of bald eagles in the United States was wind turbines. Our national animal. The hippies killed it. That's good. The irony is right. That's good, right? The hippies killed your national mascot?
How fast do the wind turbines spin?
Not very fast. They're gearing them down now, so they have a gear ratio on the inside, so the turbine generates really fast, but the blades barely spin. This is how many square kilometers per terawatt hour per year. In terms of land use. And those 4 top bars, that's biomass. So look at the energy potential of biodiesel from soy, an agricultural biofuel. Remember we talked about that? That requires 900 square kilometers. To get an equal volume of energy out of coal, you need 9 square kilometers. Yes, I did say 1%. Yeah, it's about 1.1%. You see, when we start talking about a lot of these things and you consider the land impact, all of a sudden it's like, oh, I don't really like alternative fuels. I like wilderness. So if you rule out the 4 crazy long top bars, because those are all biofuels, look at wind. Wind is 72 square kilometers. Look at nuclear, it's 2.4. Every time you see somebody going rah, rah, rah about wind power, tell them yes, but it's 35 times the footprint of nuclear power. So you got to get ready to look at a lot of turbines if you want to get rid of the nukes. Or coal, 9.7. You know, solar thermal is really close. Solar thermal's for real. That's a good one. Geothermal, that's pretty good. But when you start getting up to photovoltaic, hydropower, wind, those start eating up a lot of dirt. You can put them out in the ocean, but then people complain about the views being wrecked. Navigational hazard. Can't put in the shipping lanes. Yeah.
Denmark has wind power in the ocean.
Yeah, London has it too.
Is it pretty efficient?
Yeah.
Or is it still
Yeah.
bad for seabirds?
Well, technically the land is free. And second of all, the birds don't necessarily migrate in the same lanes, but they kind of do too. Yeah, I mean, birds follow wind patterns. The way that you and I see a freeway, they see the wind. Kind of. Not really. Okay. What I mean to say about energy is that it's not necessarily easy to balance all these different costs. I can tell you one thing that is easy, and you should remember this because I've said it before. What's the one way to solve all these energy problems?
Decrease.
Decrease demand. Use less. When people are always scrambling to figure out how to supply more, I want to remind you, you can just go, wait, what if I just use less? Remember that solves the climate problems right now. That frees up land the second you do it. And coincidentally, you save money without any of those other separate costs. And did I mention that you have more money to buy drugs and pornography and video games? The things that matter in life. Yes, dog food and beer, that's right. What Americans really need.
What kind of energy is bringing trash?
Oh, trash.
Like what kind of energy?
I don't think it falls into any of those.
That's like severe pollution.
We'll talk about this in unit number 10. It's possible to burn trash. The question is more about how you separate all the different trash sources than anything else. Because you can't burn raw trash. That's not like grabbing this stuff and burning it. They separate it into a whole bunch of different channels first. All right. Those of you that have other exciting conversations should please take them somewhere else. I encourage you to start a separate sheet of paper for the fundamentals of chemistry that you will need for this unit. We're getting into 7.5. And look, while you're getting your paper out, I have to explain that number one, I hope you'll hear me, we have 2 excellent chemistry teachers on this campus. I'm not one of them. I am neither one of them. Whichever one of our excellent chemistry teachers you choose, they can explain chemistry far better than I. I've been doing this for many, many years. So what I can do for you is I can give you a Band-Aid. A bridge to take you from totally ignorant to just barely enough to understand the details you need to know in environmental science. But there's a whole world of chemistry that explains the universe, and I can't help you with it. So please remember, I am not a substitute for a qualified chemistry instructor. Those are here on campus, Ms. Rivera and Ms. Park. Either one of them can help you with all this stuff. And personal stuff aside, they're both actually really knowledgeable about chemistry. Second, I'm going to try to do this really, really slowly in baby steps, but I assure you, these baby steps are required to get to some really complicated details later. If you know everything that you need to know about chemistry, I'd recommend you at least scribble a couple of the critical terms. And if you don't know anything about chemistry, if I say it, it's because it becomes important soon. Even if you know it, you should write this down. Here we go. The Bohr atomic model has electrons spinning around a nucleus. Nucleus just means something at the center of something else. Technically, there's a nucleus in your cells, that's different. And a nucleus of an office building, that's different. In traffic mapping, they call them the nucleus of the traffic, that's different. This is called the atomic nucleus. The atom has 3 components. Usually I go back and forth on this, but today we're running late, so I'm going to rush. Neutrons are neutral. Neutrons and neutral. They weigh roughly 1 AMU, atomic mass unit. So neutrons are neutral, and they weigh 1 atomic mass unit. Protons are positive, and they also weigh roughly 1 atomic mass unit. If you want to get nerdy, they weigh roughly 1.007 AMU. We just call it 1. And electrons are negative, and they weigh roughly nothing, 1/2000th of an atomic mass unit, which is pretty close to 0. neutrons are almost always symbolized with a lowercase n. Protons almost always with a capital P. And electrons, every time I've ever seen them symbolized, lowercase e. Please look up like this. Neutron is neutral, proton is positive, electron is negative. Are there any questions about the parts? Oh, and please forgive me, I forgot to mention, neutrons and protons are in the nucleus. Electrons are moving around the nucleus. There's a complicated mix of forces. There's gravity, attraction, and repulsion that keep the atom together. We don't have the time to get into those. Are there any questions about this part? This is called the basic anatomy of an atom. And I'd like to help you because then we're going to move on, yes?
In the nucleus, is there the same amount of protons as the nucleus?
They're often proportional, but we'll get back to that because the exception is the interesting part. And we'll come back to that. What else? Nobody else? Is all that written down?
Like protons and neutrons, just like proton and others,
Okay, so technically, if you look at the actual matter of them, they are floating miles apart from each other. But if you look at them in the scale of an atom, neutrons and protons are closely bundled in the center. That's what we call the nucleus. The funny thing is that almost all the matter in space is actually open space. So when you look really, really closely, there's huge gaps between them relative to their actual mass. But I hate to talk about it that way because it blows the mind. So you can think of them as touching. It's an easier way to model it in our brain. Okay? Just so you know, I'm aware that that's a lie. But it's easier to think of them as touching. What else? Okay. Just so you know, please look up in the smaller stuff, like from roughly here, or maybe from roughly here upward. Neutron, proton, and electron are kind of roughly proportional-ish. But there's no rule that says they have to be the same. So they're kind of roughly proportional-ish. But if you start looking around, there's all sorts of exceptions. Those numbers are usually pretty close to the same. Ish.
The reason how much their atomic mass.
I'll get to that too. Now those numbers get further and further apart from each other as you go lower and lower into the periodic table of the elements. The really big stuff is like way out of proportion. Questions about that? Now please look up. In those neutrons, protons, electrons question, the number of protons is the atomic number which tells you the element. In other words, each element is identified by its number of protons. It's called the atomic number. Please look up. That blue number, 14 for silicon, that means 14 protons. There is no variation. The number of protons tells you the element, no exception. Yes?
So every element is just a different mixture of protons, neutrons, and electrons?
Every element is a different mixture of neutrons and electrons for a specific number of protons. But the number of protons is specific to each individual element. You know how people talk about like making gold, alchemy, where like early chemists tried to figure out if there was a way to like synthesize gold? You would have to change the number of protons to make it gold. So, please look up. number of protons is fixed for each element. It tells you the atomic number. It's usually written right there. So the number you see up there is the number of protons. When you see that polonium is 84, that means 84 protons. Are there any questions about that? These are all building blocks. I know that some of you want to say, oh, screw it, I'll just learn this when I'm in college. But you cannot pass on these. This is foundational, fundamental, and necessary for every one of you. I don't want to confuse you. I want you to ask questions. Yes?
That WH slash, you wrote that for the-
Which? Atomic number. Which element? In other words, which element is obvious? Okay, now, there's another number called the atomic mass. Sometimes people write it up here, but nowadays most modern periodic tables will write it down here. The atomic mass. Here it's written in red. See how boron says 10.8? Now, this part is slightly mind-blowing. So just write down one critical word. It is the average, critical word, mass of that element. So the protons plus the neutrons plus the electrons, that weighs something.
The atomic mass.
Mhm. The atomic mass is the average mass of the element. Average. But remember that those numbers are kind of variable, so you have to get an average. Now I'm almost done. Please look up. Remember that proton and electron have opposite charges. So when you vary the number of electrons, those are called ions if the proton and electron is not an equal number. So watch me. If I have 5 protons and 4 electrons, what is the charge of that ion? Positive 1, because there's a proton that doesn't have a buddy. That's called an ion, and it's the positive ion. Yes?
Wait, are you talking about the element or the actual, like... Wait, are you talking about isotopes?
No, I'm talking about ions. We'll do isotopes next. Look, if I have boron with 5 and 5, what is the charge? Neutral, because those cancel each other out. Not an ion. We'll come back tomorrow.